I'm Kirk Harnack. On This Week in Radio Tech, I'm joined by Chris Tobin and Tom Ray, and our guest, Chuck Lakatos. With Alaskan electricity costing up to 48 cents per kilowatt hour, AM transmitters are going green there. TWiRT is up next.
Netcasts you love.
From people you trust.
This is TWiRT.
Bandwidth for This Week in Radio Tech is brought to you by CacheFly at CACHEFLY.com.
This is This Week in Radio Tech, episode 101, recorded September 28th, 2011. North to Alaska. This Week in Radio Tech is brought to you by Axia Audio and the Axia IQ audio console. IP audio is great technology, flexible, powerful, and cost-effective. Check out the IQ on the web at axiaaudio.com/IQ. Hello, it's time for This Week in Radio Tech. I'm Kirk Harnack, your host. Glad to be here. And where's here? Well, we're doing a radio show from a TV studio today. That's where I am. I'm at an undisclosed TV studio in Nashville, Tennessee today. Got a couple of great people with us here. First of all, two of our usual co-hosts are with us. One of those is Chris Tobin, the best-dressed engineer in radio from Manhattan, New York. Hello, Chris. How are you?
Hello, Kirk. Hello, everyone. I'm doing well, and so far, so good. And I'm not in any crazy studio, just a small little office and doing our part here at the TWiRT operations.
You know, we've got our guest on this episode is Chuck Lakatos, and he's got a lot of interesting things to tell us about AM radio. And yeah, so many of us think that AM, well, how important is that anymore? It seems like in a lot of part of the country, of the U.S., AM is just not so important anymore. In a lot of countries, they don't transmit AM anymore. But our guest, we'll get to him in a moment here, our guest is in Alaska. And I can tell you AM is really important in Alaska. So we'll get to our guest in just a moment. Let's also bring in from the Hudson Valley of New York, Tom Ray. Hello, Tom.
Who feels totally inadequate tonight because my little ham shack does not compare to the studio you're in. Good evening, Kirk. Good evening, everyone. As Kirk said, I'm Tom Ray. I'm VP of Engineering for Buckley Broadcasting, WOR Radio, New York City. And I'm glad to be here.
Glad that you are here. And, well, the difference between your ham shack and this studio is you own everything in the ham shack.
That's true, but
yeah.
You know, it's not HD and fluorescent lighting.
Yeah, and I apologize for this lighting. This lighting would look great if I was turned around the other way, but there's just not a great place to do that. So my back of my head is lighted very, very well. All right, let's move on and bring in our guest for this show. I first heard this fella's name years ago, I suppose, on one of the engineering listservs. And I never knew what Chuck even looked like until I Skyped with him earlier today. It's Chuck Lakatos, and I hope I'm pronouncing his name right. Chuck, are you there?
Yes, I'm here, and you've got my name, and you get an extra bonus point for that.
Okay. Well, Chuck, you are associated with Alaska Public Radio. That sounds like a big job because it's a big state. What do you do there?
I'm Director of Engineering for Alaska Public Broadcasting. We've got... I primarily take care of the radio end of it these days, and we've got 30 radio stations in the state, and we're also responsible for a low-power television network with 208 village translators, which keeps us busy. We've got 6 10-kilowatt clear channel AM transmitters that just, at least one of which has to generate its own power with diesel fuel at $6.50 a gallon at 23 gallons a day. So we realized a couple of years ago, if we didn't find a way to control those power costs, we were just going to have to shut off the AMs. And we didn't want to do that because, for instance, the North Slope Borough in northern Alaska is an area of 89,500 square miles. By the way, a borough is the equivalent of a county.
Yeah.
89,500 square miles is a size of a little bit bigger than the state of Minnesota. And the only broadcast service at all, commercial or non-commercial, in that area is the 10 kilowatt AM transmitter at Barrow, 680 on your dial. There's really no alternative to this kind of a service in this part of the world.
So with all this AM coverage and a lot of it, reasonably high power at 10 kilowatts each transmitter, as you alluded to, you guys burn up a lot of electricity in generating these AM signals that do travel quite a distance, but that's kind of necessary in a big state like Alaska. But you spend a lot of money on electricity or a lot of money on fuel, and that's what the subject of this episode of This Week in Radio Tech is about. It's about a technology that's not altogether new, but there's more variations of it now. They're using it in some other countries, and it's just now becoming allowed to be used in the U.S. And it's this notion of, in addition to modulating the sidebands, or providing amplitude modulation, thereby creating sidebands on an AM signal, you're also able to dynamically control the power that's in the AM carrier. And this is pretty interesting. Of course, we do that anyway when we modulate a signal, when we apply amplitude modulation to a carrier. But we're also talking about now something in addition to that modulation to control the carrier. So, Chuck, maybe you can kind of carry us through that process. Give us the reason why this was considered. A goal here, saving electricity, but then tell us what's happening here to make these AM transmitters use less of this very expensive power in Alaska.
Of course, this started about 15 years ago, actually, in Europe. Originally with Siri Brown Boveri, and then later with a couple of other European broadcasters, and then eventually the British Broadcasting Corporation. This technology was first applied to the really high power long wave and medium wave stuff. For instance, right now it's being used by a 2,000 kilowatt Voice of America transmitter in Bangkok, where they have to generate their own electricity. I think $6.50 of diesel fuel for my 10 kilowatt kind of pairs in insignificance, trying to run a 2,000 kilowatt transmitter. I'll go briefly into the algorithms. The first algorithms were generically referred to as dynamic carrier control, and at zero modulation, these systems tend to reduce the carrier level about 6 dB, and then using various algorithms, as the modulation increases, the carrier increases at low levels and then is dynamically controlled. You'll usually get your choice of 3 or 4 curves to choose from. These systems will show a power saving of about 35%. I chose a rather different one developed by the BBC called AM companding. With the BBC algorithm, at zero modulation, you have full carrier. At 10% modulation, you start to see a reduction in total power. And at 100% modulation on a power meter, you'll show half power. So on our DX10s with no modulation, you'll show 10 kilowatts. At 100% modulation, you'll show 5 kilowatts.
Now, let me make sure I understand with that the one that you mentioned, is it AMC?
Yes, AMC.
Which stands for amplitude what?
Amplitude modulation companding.
Okay, amplitude modulation companding. Okay. With that system, so the more modulation you do, the carrier is brought down, but the power in the sidebands is not brought down, is it? That's
right. And
okay.
The advantage, the reason I chose AMC is that our programming in Alaska is very diverse. I sometimes call it 1935 programming. You'll get a news block, and then you'll get a radio block, and then you'll get another spoken block. So many of our rural stations, believe it or not, besides carrying what you might consider the regular public radio programming, might have as much as 35,000 songs on the hard drive.
Wow.
And they do rock and roll. They do a lot of country. They use, the program directors will use Selector. Program, the traffic people will use something for traffic to sell the underwriting. So those stations have a really wide format. The advantage of having the BBC is that with low modulation levels, the high carrier level keeps the channels quiet. You'll find that with the other types of modulation, at low modulation levels, you might hear a little bit more noise in the noise floor, but not very much. My other reason for choosing AMC is that when you start really changing the power levels in these transmitters, you get significant instantaneous changes in the AC utility current. And generators tend to not to like that. So
okay.
So also I found out that some utilities now, the substations, are regulated by tap changers, solid-state tap changers. And some utility substations don't like to see rapidly changing current. So that's the main two reasons I chose AMC. It's tended to deal with the varied formats of our stations a little bit better than the other ones. It keeps the channels quieter on low levels of modulation, for instance, classical music, and it tends to not have as dynamic change in the AC to utility current.
Well, that makes sense, because if you're modulating a lot, your transmitter is putting out plenty of power in the sidebands, so that's the opportune time to reduce the carrier. So you get more consistency. Okay, that's a bit like having a tower light system where half the lights are on at one point and the other half of the lights are on the other point, which I don't think is proper anymore. But that way you kind of keep a balance going there. Now, if you're programming, if the audio that you're sending tends to be very active and have a lot of modulation, then it also seems like AMC, the companion that you're talking about, would be appropriate. But if you're running programming where there's a lot of dead air, a lot of quiet talk, then it may not be the best choice. Would I be right about that?
Yeah, that's right. I think the thing to do is you might very well want to try various algorithms. It's easy to do with the Nautel because the six algorithms are built into the Nautel, and you can activate those by contact closures on the rear of the thing. So you could, from a rote site, change the various algorithms and listen to it. The Harris unit requires that you change a chipset for each carrier control algorithm. So it's not quite as easy to change algorithms with a Harris as it is with the Nautel. But there's definitely a power savings. We have had one Nautel XR12 transmitter in service with this AMC companion for about a year, and the power savings are about 27%. That is in a town, Dillingham, Alaska, where the commercial electricity rate is 48 cents a kilowatt hour. So they're saving a ton of money. Wow.
Can anybody do the math on that? How much power is that in a month or a year, and then how many dollars would that end up being?
The party at Nautel, if you go to the Nautel site and do a little search, you'll find the presentation that he did at the NAB a couple years ago, and he was showing that pretty easily at a typical a typical 50 kilowatt station in the U.S. with typical utility bills that we'd be saving about between $20,000 and $25,000 a year. Considering that the technology only costs about $3,500 to implement, that's pretty much a no-brainer.
Wow, yeah, pay for itself in the first month or month and a half or so. Hey, let me bring Chris and Tom into this. Now, by the way, Chuck, you said that you were running your AM transmitters tend to be at the 10 kilowatt power level. Did I get that right?
Yeah, that's right. We've got almost all of them at 10 kilowatts. We do have a 1 kilowatt AM transmitter and a 5 kilowatt transmitter. And I'm not going to convert those because the equipment is not available. However, last week, a religious station in Nome fired up a DX50 on carrier control, and it looks like their power saving is going to be about 30%. Interestingly enough, their contract engineer lives here in Anchorage, Terry Reynolds, and with a general coverage receiver, he listened to their Skyway and tried various AGC settings and heard very little difference in the audio between regular AM and the AMC companded. unless he turned off the AGC on his receiver. Then it was pretty obvious that something was happening.
Oh, yeah. Yeah, I guess, yeah, there's that receiver AGC. And, hey, in fact, I want you to explain that in a little bit, because on this show, we really haven't talked much about receivers. But with both AM and FM, there's some AGC in the receiver. We'll get to that in a second. Tom Ray, I want to ask you, you and at Chris's, the stations that Chris used to work at, you guys running 50 kilowatt AM transmitters. Tom, at WOR in New York, dare I ask what your typical monthly power bill would be there?
Typical monthly bill, and it depends on the month, from the very simple standpoint that PSE&G, Public Service, Electric and Gas in New Jersey, in the summer adds a surcharge because it's summer and they can. But the typical bill runs about $10,000 a month.
Wow.
That's for the transmitters and, of course, the tower lighting. So, heck, if we could save 30%, and I've already been talking to Harris about this because there is a concern as to whether or not it will destroy the HD radio signal. We're going to try it at some point and see what happens. But, you know, some of the people watching and listening may be wondering, they may be sitting there going, well, okay, wait, time out. Whoa, you're reducing the carrier level. Why? How can you do this? And, a number of shows back, we had a little discussion about, oops, and I hope I'm still up there because my video is frozen.
Yes, you are.
Anyway, okay, good. No, we had a discussion about modulation and about AM, and one of the things I had said at one point was that AM is a mixing process where you take the carrier, you mix it with the audio, and you get the sidebands. The sidebands are where the information is. Those of us who are ham operators have known for a long time that you don't really need to transmit the carrier to recover the audio. The carrier is good for two things. One, it helps generate the sidebands, and on the other side, it regenerates the audio. So if you inserted, what we do with single sideband is if we insert a carrier internally from the on the radio, we regenerate the audio. We hear the audio because the radio is just picking up the sidebands that are transmitted. That wouldn't really work too well eliminating the carrier, because the radios we have out there rely on that carrier, A, for reference, and B, to lock on the signal when you hit seek. But reducing the carrier under modulation? Oh, heck yeah. Why not? Because once you've got the reference, if that carrier is coming up and down, it's not really a big deal. You should be able to, with the AGC and the radio, you should be able to hold on to the signal. And I imagine you wouldn't hear much difference. So I'm looking forward to playing with this.
Tom, I will tell you that Terry Cockrell at Harris, about 10 days ago, was able to put AM HD and AMC companion on a DX10 in their labs, and it met the mask perfectly well. And he didn't. He just then in their HD instruction lab, he just grabbed a couple receivers, I think, and a Curian and an old Boston Acoustics, and he just plugged them in, and they worked. He did. He couldn't do any testing at the time on signal levels, et cetera, et cetera. Tim Hardy, Director of Engineering for Nautel, told me last year he didn't see any particular reason why they couldn't play together. At the transmission side, his question was how the receivers would act. And my decision was, well, fire them up and get some receivers and see if they work. Rather than,
well, Chuck, it's funny you say that, because what I told Harris, I've been talking to them about this, and they would actually kind of like to use us as a test station for it. And I said, let's go, because I know where our HD radio signal covers. Let's go. Yeah. I can tell you if it's hurting it right now.
Yep. So I'm interested in it particularly because we have one of our 10 kilowatt stations has a translator about 50 miles away. And for many, many years in Alaska, we have been allowed to take off the air AM signals and use those to drive FM translators. And we have a community in Cordova that for, probably the last 2 years has been using the HD signal to drive their FM translator with a tremendous improvement in audio quality, of course, because they're not translating the 5 kilohertz bandwidth limited AM. So I said the thing to do is try it. Let's buy some receivers and see how it works.
Hey, have you found the AGC for AM receivers to be a challenge?
Not in the one test that we've done. I've been told by a BBC engineer that years ago, about a decade ago, when they did this algorithm, they bought 100 receivers and checked them out and came up with a time constant that they use. And BBC said, well, the AGC's time constants have been the same in AM receivers, no matter who manufactures them, for decades. Terry Reynolds, when he was listening to the 50 kilowatt station in Nome last week on Skywave, he had a general coverage receiver, and he tried various AGC settings on his receiver and didn't notice any change at all in the audio quality until he just turned the AGC off, and then it was pretty obvious. He could see a big change. But,
most AM radios, you don't have the luxury of turning off the AGC, so that's a good thing.
So I don't think there's a problem, and this technology was developed by folks who are really, really good, audio and AM engineers. The BBC are a pretty sharp bunch of guys, and I was pleasantly surprised when we first tried it. My main concern, more than the audio quality, has been what's going to happen to the AC utility voltages and the generator voltages. I would suspect that if you have like a 50 kilowatt transmitter, it comes time to use emergency power, that you might want to use some auxiliary contacts on the transfer switch to kick your your exciters to the bypass on a Harris or to the AM mode on a Nautel.
Now, that's a little confusing to me that you would suggest that, Chuck, because I was under the impression that with the AMC companding in, your load would actually be more steady than without the companding kicked in.
Yeah, but there's still the instantaneous changes, that you're not going to see on the power meter, but you're going to see the voltage regulators. The modern voltage regulators are going to see those. But there's definitely less of instantaneous current changes on AMC than there is with the other algorithms. And I verified that with a Fluke power analyzer, and Tim Hardy had told me that Nautel had confirmed that a long time ago.
So here's a question, on our show that we did a lot of episodes back about how amplitude modulation works. We learned, we talked about the fact that we're imposing information upon the carrier, or we're getting the carrier to carry information because we're changing its amplitude up and down, up and down, up and down, louder and stronger and weaker and stronger and weaker at the rate of the audio that we're carrying. Well, if we use any of these, either companding or DAM or any of these methods to change the carrier power, why is that not affecting the audio? Why is that not itself carrying information along? And my first guess is because it's done at a rate that is far slower than subaudible audio. In other words, this is not a fast modulating process. This is a down and up and down and up and up and down and down and up.
I'll point out something that all of these algorithms, whether they're the AMC or the various DAM, ACC plus technologies, do something very interesting. The carrier level is always represented by a DC voltage, and the amplitude of the sidebands are developed by a rapidly changing, AC voltage, which brings up some rather interesting things when you do your first adjustments. You'll have an audio gain control on a DX50, for instance, that suddenly has both audio and DC running through it. So you have to be careful when you start tweaking things, because you might say, oh, I need a couple dB more of modulation, and you tweak those things without thinking about it. And suddenly you realize, my modulation looks great, but now instead of 10 kilowatt carrier, I've got 12 kilowatts. As long as you just keep your wits about you, you won't have that problem. But
well, that's a great point. This whole thing becomes if you're trying to set a modulation level, it seems like this whole thing becomes a bit of a sloppy moving target. How do you set modulation level when changing the modulation changes the carrier, which is what the modulation monitor is referencing to give you the modulation level?
Actually, first of all, you cannot use any of the existing analog modulation monitors because the carrier's changing. So first of all, the carrier alarm light's going to be flashing on and off, and you're going to lose the peak reference, so your modulation monitors will look very odd. The only modulation monitor that I know of that will look at these algorithms is the Bell-R Wizard. And Bell-R Wizard has had the ability to take care of these various algorithms for quite a few years because Bell-R had to meet the needs of their foreign customers that demanded monitors that would work with AMC and DAM and DCC. Those modulation monitors, by the way, list at about $3,500, and you see the price around $3,200. The last I checked, delivery from Nautel was, or a delivery from Bell-R was about 10 days to 2 weeks. I also will tell you that the day that after the FCC made the ruling, Terry Krause at Nautel and Jeff Mendenhall at Harris told me they were absolutely deluged by inquiries. So I would suspect that if people start putting these things in, that the lead time to buy it, to get a Bell-R Wizard delivered to your station might go up considerably. I've done all my installations using oscilloscopes and all my monitoring with an oscilloscope. And I was told by Steve Lockwood of Hatfield and Dawson that whenever he's been into foreign sites, the engineers there just use oscilloscope monitoring.
So what's your technique with an oscilloscope if your carrier's moving around? What do you make a trapezoid pattern, or how do you do this?
Well, you can do that, but what I have found works just as well is you get things set up with 100% modulation with just regular AM, and then you switch on either the Nautel or the Harris. Use your oscilloscope, and what you're going to find is some pretty good horizontal white lines where you're exceeding 100% negative modulation. And then I just back up the audio processor a half a dB at a time until those go away.
Okay.
And that seems to correlate with stuff. We don't do much asymmetrical modulation, plus 125, et cetera, because the audio sounds wretched when you do that. I know the commercial broadcasters do it, and that's something for commercial guys to experiment with. But I've had really good luck. One of the things I will tell you is that public radio listeners, as a rule, are the first people to complain if they detect lack of coverage or degradation of audio. We have had no telephone calls that I know of where people have said, "Oh, I can't get you," or "Your audio sounds terrible." I don't know of any way of our AM stations to do anything like a partial proof or anything like that because, there are no roads.
There's no roads.
Hotel would like to hire a helicopter for me so I could fly out radios. That'd be an interesting experience. But we have, as a practical matter, we haven't received any complaints from listeners about audio quality using AMC, or any problem where people from a fringe area say, "I can't get you anymore." So.
And you yourself said that, or you reported, and also your engineering friend who lists the station far away reported that he didn't hear any problems caused by this AMC with the carrier going down by as much as 6 dB when the transmitter's heavily modulating. So I'm guessing if you can't hear it, if another engineer can't hear it, it's not so likely you're going to get complaints from listeners either.
Now it's interesting that AMC, the maximum reduction is 3 dB or half power.
Oh, okay, half power. Okay.
With some of the other algorithms, you can go as high as 6 dB reduction. Interestingly enough, the only two curves you get with AMC, one is called enhanced AMC, and its function is not to reduce your power bill, but to actually get more power out of a transmitter. So, for instance, if you have a 10 kilowatt transmitter and you go to eAMC, you can have a 12 kilowatt transmitter. I think that's used primarily by foreign broadcasters that were trying to get the last kilowatt out of their 100 and 200 and 500 kilowatt rigs. I've never used it, and except one time by accident when I went, oh, wonder why I have my 10 kilowatt transmitters making 12. All the other algorithms offer several curves. They're all piecewise linear curves. That is, they're straight lines, and at the low levels of modulation and the high levels of modulation, that's where the breaks and the curves tend to happen. And I think it's just going to be a matter of trying out these various algorithms with your particular format and your particular coverage area to see which one you like. But the power savings are there. Some people have reported savings as high as 35%. I think that maybe if you really tweak things, you might get 32. 30%, I think, is going to be more typical.
Yeah. Hey, when we come back from our break, we're going to give you some resources online. There are articles in Radio Mag Online, Radio World, and other places that you can read about this technology. And I think it's probably pretty helpful to have a look at the waveforms that result from this, and it can kind of give you a better idea of, oh yeah, that's where the power savings is coming from. That's when the transmitter's putting out less power. But first, I want to tell you about our sponsor on this show of This Week in Radio Tech. It's Axia Audio. Now, folks at Axia are also my employer. Well, that's a good thing. You might think there's a relationship there. Well, there is, but it also means that I know a lot about the product I'm going to tell you about. Axia Audio is the pioneer and the leader in IP audio consoles. And we were making IP audio consoles 7, almost 8 years ago now with the original Smart Surface. Well, one of our most recent consoles at Axia is the IQ console. I want you to check it out. Go to axiaaudio.com/IQ. We call it the console for those who think for themselves. Okay, I'm not exactly sure what that means, but it does have a lot of cool things involved with it. The IQ is expandable. It starts out as an 8-fader console. It has OLED displays for the metering, for the clock, for the timer, and each channel strip has its own little OLED display that clearly shows you the name of the source that's on that channel strip, and it can tell you some things about that source. Like there's actually little confidence meters on that OLED to show you there's audio coming in, even if the fader is turned down. It can tell you about the status of that source, whether you can talk back to it or not, for example, whether the source is muted somehow, whether you have control over that source from your fader, or maybe another console at the moment has control over some shared resource. Every channel strip has, at the top of it, instead of a button, it has a rotary knob that you can grasp that knob and either change functions on that channel strip. You can change sources if you like. You can change it from stereo to mono or left only or right only. You can also do a real quick gain trim with the knob at the top of each channel strip. So if you've got a source that's coming in too low or too high, just grab that knob at the top of the channel strip and select the function you want, twist it, and you'll get the function that you want to accomplish there. The IQ console is expandable. So if 8 faders is not enough for you, well, it's easy to add more. There's an expansion module that is 8 more faders. So you can add up to 2 of those and have a 24-fader console if you like. You could also add we have a couple of 6-fader modules. There's 6 faders with user buttons. If you need some GPIO control out the back of the rack mount unit and you need it from the top of the console, there's 10 buttons there, 2 strips of 5. There's also a 6-fader expansion that has a phone controller built right in. It gives you control of 2 hybrids and 6 lines, and we intend for you to use it with the IQ, the Telos IQ6 phone system, which is 6 POTS lines, and it all works through Axia's live wire. So you don't have a bunch of analog or AES connections to plug up. You just took a live wire Cat5 connector to it and plug that into the Ethernet switch. The Ethernet switch? Yeah, the IQ has an Ethernet switch built into the back of it. So you can add more Axia nodes, or it also has some PoE, power over Ethernet ports. So you can add some new Telos VSET telephones and have them powered right from the console. The IQ console has 4 mic inputs with selectable phantom power, so if you need to use a condenser mic, there you go. 16 analog inputs, has 2 AES EBU inputs and 8 analog outputs, and 2 AES EBU outputs. Plus there's 8 GPIO machine control logic ports. Each of those has 5, each of these 8 ports has 5 opto-isolated inputs and 5 collector-to-ground outputs. A bunch of features on this console. I tell you what, we have shipped, I want to say, close to over 200 of these consoles now. We've just been shipping them at Axia for about 3 months now. So I'd like you to check it out. The IQ console at axiaaudio.com. I think this thing is just amazing. And my next console at my radio stations is going to be an IQ. Or maybe a radius. That's a whole other subject. Leo has a radius. The IQ is expandable, and the radius is strictly 8 faders. Check it out, axiaudio.com/IQ. And I have an announcement for you. I told you earlier in the show that we were giving away something pretty cool tonight. There's a function going on tonight in Columbus, Ohio. It's the SBE National Awards, and several fine engineers were recognized there and given the SBE's highest award. But at the dinner, Telos was there represented, and we gave away a door prize, and it's a Zip 1. This is the IP audio codec. It works over the internet. Pretty cool little box, the Zip 1. And Art Lieberman from KGO won the Zip 1. So congratulations to Art Lieberman. Glad you were in attendance there, and we certainly appreciate you and all the others in attendance in Columbus at the SBE meeting. Okay, let's get back to talking about AM transmission and how we can save a lot of money on the expensive electricity that it takes to run these transmitters. Our guest is Chuck Lakatos. He's the Director of Engineering for Alaska Public Broadcasting. And my 2 co-hosts with me are Chris Tobin with Musicam USA, and also Tom Ray with WOR and Buckley Broadcasting. So here I've been yapping along a long time. Tom and Chris, I know you've got questions for Chuck about this technology that lets an AM transmitter run using a lot less electricity, like upwards of 30% less. And when you got a $10,000 a month power bill, or even more than that, where electricity costs so much in Alaska, particularly, you can save a lot of money. So, hey, Tom, let me turn it over to you and see if you've got the next stab at a question for Chuck Lakatos.
Yes. As a matter of fact, I know that Chuck has a Nautel, and he knows that someone who just turned this on in the Harris. What's involved in putting it in, Chuck? Well, what do you need for equipment? For example, with the Nautel, is it just part of the software load, or do you need external equipment? And what's involved, and how difficult is it to put it in and get it tuned up?
It depends on the Nautel transmitter. You can use this technology on the XL series, the XR series. I think it's now built into the NX series, 25 kilowatts or above. And you can convert certain versions of the old ND series. That depends on the serial number of the transmitter. I actually have a Nautel unit here, and since we're talking about that, let me get my little camera over here. It's going to be a little crappy, guys, so excuse me. Let's see, I'll just brace it right here. The Nautel unit is actually one of their single rack unit AM IBOC generators. They pull the X-Gine card out of it and put a digital signal processing chipset in here that will allow you from this front panel to select any one of six carrier power-saving algorithms, and also just regular AM. So basically, it's kind of an all-purpose signal generator. It also has the ability to have an AES input or an analog input, and you can set those analog, those inputs to be your primary or your fallback, if you lose the audio from one. You set your frequency in here. It also has a gain control adjustment. Pretty straightforward, and significantly easier to do than the Harris. Last year, the Nautel units look quite a bit like the Harris one I have here. I'll show you in a minute. But when I really got interested in this, Tim Hardy said, we can do all this in a DSP chip. They pull the X-Giant card out of here so they don't have to charge you $5,000, ubiquity licensing. It's pretty straightforward. I found as the first user to find 3 or 4 minor glitches in it in the display, and Nautel was taking care of that. In terms of the transmitter, and the Nautel, if you already have an iBox installation done, like you obviously do at your station, basically you don't need anything changed. You don't need anything changed on your Nautel transmitter. If you have an analog Nautel besides this DCC box, you're going to need installation, the little iBox interface card where you have magnitude and phase, and you'll have to change out the PDM card. And then it takes about an hour of adjustment to get things tweaked properly. So it's fairly straightforward on a Nautel transmitter. The Harris unit, which I'm going to show you here right now, is a more traditional kind of deal. This is about a 9 by 9 inches to the plate on one side. It's probably 8 by 8 on the side. You see that this is the remote control to turn the thing on and off. This is right here is the replaceable chipsets. I think the chipsets are about $100 to $105 a piece. Those have to be changed for each algorithm. The audio input goes in here. It's all analog. The audio, there's 6 individual audio outputs to feed, day-night transmitters, etc. If you have an HD DX transmitter ready to go, or a 3DX transmitter, there's very little you have to do to anything in the actual transmitters themselves. So I think the installation is fairly straightforward. I will tell you, the first one that we tried to do, the first Harris here, we got 90% of the way through, and then we didn't have any audio, and it turned out this little chip right here, it's a programmable chip, and the assemblers forgot to program the chip. Actually, the assemblers programmed the chip, but the assembly instructions did not say to do a checksum on it. And if they had done that, they would have shown the checksum failed and the chip wasn't programmed properly. That's about the only trouble we've had with this. The Nautel, out of 3 units, I had 1 unit that died. The exciter just died for some reason while we were doing the final adjustments. And Nautel said, rather than worry about which part of the system failed, they just sent me a whole new kit I'm going to be installing next week. I would estimate the first time you did this, it's probably going to take you, on the Harris, maybe 4 to 6 hours, because you got to drill some holes and mount some cables and stuff. If you have an iBox transmitter, iBox Nautel transmitter, and you run this, I think you ought to be able to get it going in about an hour, hour and a half. So it's pretty straightforward. Both transmitters. The Nautel's a little bit flexible, more flexible. By the way, I believe that I could use a Nautel exciter on a Harris DX series. I gave it quite a bit of thought looking at schematic diagrams. I decided not to do it because I didn't want to have manufacturer's finger pointing if something went wrong. So that's about it. It's fairly easy to install. It's a pretty mature technology. I had a little bit of problem with Harris at the beginning. They rewrote the manual because, of course, they assigned their domestic field service guys to help me, and I think it probably would have done a lot better if they had originally assigned me one of their offshore guys who've done this a lot of times. But there's nothing magic about it. I looked at it with my spectrum analyzer after I did this. It meets all the NSRC stuff, occupied bandwidth, et cetera, et cetera. The only thing I didn't do on this was see how asymmetrical positive modulation works, because I don't use a lot of that. By the way, if you're interested in that, Susan Stamberg has the most negative asymmetrical voice in the entire history of broadcasting.
Is that right? Susan Stamberg, a very famous host on National Public Radio.
Yeah, look at an FM modulation meter, and you'll just see the negative side just really moving. It's just pretty amazing.
Oh, my goodness. Who would have thunk?
Yeah, questions, guys?
Chris Tobin,
I know.
yeah, you've taken care of a
yeah.
lot of AM transmitters, Chris. Go ahead.
Oh yeah, yeah. Well, especially here in New York City, with the canyons and re-radiation from overpasses and bridges and whatnot. Any reports or any studies done with re-radiation of the AM signals, and during this process, anything noticeable on the receiver side, or I mean, so far it sounds like I've been reading the BBC paperwork while we're all sitting here talking and listening, and it's a very robust algorithm in the approach, and actually I'm quite keen on it. Just curious about re-radiation, how sometimes it wreaks havoc on certain technologies. Any talk or any studies with that?
Well, where I put them on, there's nothing but miles and miles of miles and miles.
I know, that's what I thought.
In Barrow, it's 250 miles to the foothills of the Brooks Range. So I do have one in McGrath, which is fairly close to 10, and there's a lot of really crappy, really bad power lines running around, and we drove around in nothing more sophisticated than a station truck listening to the AM radio on it, and didn't seem to have any problems. I think the BBC algorithm is the most robust of all. That doesn't mean that you might find one of the other ones useful for your for your purposes. But I'm really satisfied with the AMC algorithm, at least in my case.
No, I would agree. I would agree. It makes sense. And reading it definitely is very aggressively designed, and it makes sense. And from a standpoint of saving money to to justify your operation, this is definitely an approach that's worthwhile. And if you're talking, less than $5,000 in some cases to make the investment, if you already have proper transmitters, it's pretty good. And I know Tom and I, in my previous jobs, the places our power bills were definitely something. As Tom puts it, during the summer you get charged more because you can, and if you decide to run your transmitters and dummy loads and stuff, the peak load changes the monthly bill as well. So this makes total sense to investigate.
Yeah, I was at a site years ago in another life where if we tested the standby transmitter, we used the generator. Otherwise,
absolutely.
You got a surprising increase in your power bill for that month.
Absolutely.
So I think this is worthwhile. It's not a new technology. It's been around for 15 years. In fact, Nautel and Harris both told me, you just can't sell a transmitter offshore without this technology.
Oh, really? So they need to have that in their transmitters they sell outside the U.S. People want it that much.
Well, because they tend to be so high power. You look at these long wave. You look at these long wave legacy stations, they're 200, 250, 300 kilowatts, sometimes as high as 1,000 kilowatts in the Far East. So,
gee,
you're serious power bills there.
Yeah, so if you can save 20, 25, 30% off a megawatt, well,
yeah.
That's now you're talking some money here.
Yeah. And with AMC at least, I haven't had any complaints of the power problems. To tell you honestly, the other algorithms we didn't run long enough to maybe let people listen to them for a long time, because I very quickly decided that with our format, where they play things like jazz and classical music, and talk shows that that are not screaming sports talkers, that there was going to be a lot of low modulation levels, and I wanted the channel to be kept quiet. This is why I picked AMC. You guys may want to do something else.
Yeah, and let's touch on that for just a minute in our remaining minutes here. Chuck, you said you wanted the channel to remain quiet. Help me understand why that happens. Why do you want a good, strong carrier when there's no audio?
Because the carrier keeps the presence of carrier keeps the AM the audio on the AM receiver quiet. I mean, I could imagine to be turning your radio receiver away from the AM station, you're going to hear all this very significant AM noise in the background. Particularly in urban areas now, where the RF noise floor is just skyrocketed because of the 5 million cheap Chinese fluorescent light pictures and that sort of stuff.
And this change in noise, and this is also a well, if you have an AM radio that if you can turn off the automatic gain control, then I guess you'll have a pretty linear relationship between the amount of carrier coming in. Let's imagine it's unmodulated carrier coming in and how quiet the receiver is. The more carrier, the quieter the receiver. If you've got AGC there, I would imagine there's a bit of a nonlinear relationship between these two things. But once the incoming carrier gets low enough, then the noise really comes up as the AGC gets very noisy.
Yeah, with AMC, I didn't notice any pumping or anything like that. A typical radio receiver I would look at with, let's see, I've looked at Ford trucks and GM trucks, Focus, our GE Super radios, which every public station in Alaska is operated as premium one time or another. I think about 25% of the radios in rural Alaska are GE Super radios. We've had very very good luck with these things. I'm very pleasantly surprised. I thought for sure I would hear much more artifacting than I ever have.
So you were apparently pleasantly surprised by the lack of artifacts, and then you're obviously enthused about what it's going to do for your power bill.
Yeah, Tim Hardy at Nautel and Jeff Mendenhall at Harris both said, "Oh, we can almost bet money on it right now that you'll choose AMC, just as the basis of our format." And I find it interesting. The BBC, like their overseas service, their formats are quite a bit like our public radio AM. You hear the BBC News, and then you'll hear a rock and roll show, and then someone will talk about, keeping the crocodiles out of your garden in Nigeria, and then more music. So that algorithm fits me very nicely, and I think it would fit a lot of people. I've listened to this algorithm on the typical things like Talk of Alaska, and also the infamous birthday programs. Every public station in Alaska has birthday programs. Oh my
goodness, didn't know that.
They're incredibly popular in rural Alaska. It's the equivalent of polka time when I used to work in Iowa and Kansas.
Sure. Hey, we're going to run out of time here in the next few minutes, but Tom, Ray, do you have a final question or thought for Chuck?
No, actually, I found it very interesting, Chuck, and I'm looking forward to getting my hands on this because God knows we could all stand to save a couple of bucks in the way the economy is these days. So that sounds it sounds interesting, and thank you for being one of the U.S. pioneers in that.
Yeah, thank you very much. I was pretty amazed. I was out in the field finishing a install 2 weeks ago, and someone called and said, "Hey, do you know that modulation dependent carrier level has been approved?" And I went, "What the hell is MDCL? Have I been sandbagged?" And then the attorney said, "No, the FCC had to just change the abbreviation to make it work because all."
These other names are trademarked or patented, right?
Yeah. So that was a quick invention of the FCC when they wrote up the new notice.
Modulation dependent carrier level, MDCL.
Yeah, there's lots of literature out there on it. It's been very, very well tested by all the broadcasters. I think the only reason it's never been adopted in the U.S. is, let's face it, electricity's been cheap here, and it's not going to be cheap anymore.
Yeah, well, imagine if you're an engineer being able to walk into your general manager's office or your owner's office and say, that $8,000 a month power bill or that $12,000 a month power bill that we pay at the transmitter site, I can save you $2,000 a month on that. Are you interested? And hey, pretty soon that engineer who usually looks like a black hole where money goes, all of a sudden some money's going to come out. You save the station a lot of money. Chris Tobin, do you have any last questions, comments before we have to go?
No. I was actually just going to say, in your opinion, if you're a station owner, operator, or an engineer, and you're looking to keep the budget in check because, finances are what they are, this would be a technology for an AM station to consider, especially if you're the only game in town and you're just trying to stay competitive. I mean, that would probably make a lot of sense from what you've seen as far as the cost of ownership, installation, and overtime.
Yeah, I think it's true. The capital cost on this thing is going to be a lot less than $5,000. I think
Yeah,
ours
that
ran
makes sense.
$3,800. And that
Oh,
installation.
you're absolutely right.
The technology doesn't care whether it's a 10 kilowatt transmitter or a 50 kilowatt transmitter. It's the same circuit card, the same DXX decider.
Okay, you're right. That's a no-brainer. Do the math. You're right. You're absolutely right. Okay, great.
Hey, in the chat room, they've brought up at least one good link, and I made my own Bitly link to it that's easier to remember. It's a PDF that's on the FCC's website. It's at transition.fcc.gov. But here's the Bitly. It's a lot shorter. It's bit.ly/AM carrier. And I made that lowercase. So if you go to bit.ly/AM carrier, you can read all about this. This is a letter from Tim Hardy of Nautel and a presentation that Nautel made at the NAB show. And the FCC has this on file. A lot of good detail there, and also in a pretty easy to understand format. Chuck, quickly, you have a last comment for us about this. What'd you call it? Dynamic. You had a word for it.
Carrier control.
Yeah. Okay. Done. That's one word for it. Yeah.
My last word of advice to the engineers is be really on your toes the first time you do this, because you're going to do the same thing I did. You're going to say, "Oh, I need a little bit more modulation there," and suddenly you realize, "Uh-oh, the carrier's a lot hotter than I want it to be." I'll admit, when I really did it, I found out that all the overload relays on the DX10 power amplifiers work.
Ah, okay. Gotcha.
Okay.
All right, guys, we have got to go. We're out of time. Kirk has to go, and I sure appreciate the good comments and questions. And Chuck, thank you so much for taking some time out of your afternoon there in Alaska to tell us about the pioneering efforts of this technology, which you said has been around 15 years, but not in the U.S., not until now. So I appreciate your time, Bill, and I hope you'll come back on the show sometime.
Thank you much,
I'm sorry,
guys.
Chuck, not Bill.
Yeah.
Go ahead.
Well, just thanks a lot, guys. I'm really gratified that I thought that maybe they'd end up the FCC just allowing us to do it in Alaska, but Ann Gallagher is the one who should be encouraged. She's a breath of fresh air at the AM branch. I was just ready to do all kinds of proposals, and she said, "Yeah, looks good to me. I'll give you 2 experimental authorizations." And it's been less than a year later that she says, "Yep, just write a letter. Go ahead, do it. It works."
Yeah,
Well,
AM broadcasters don't realize that she is really an asset. I've worked with her office and she's done stuff for us with places I've been in the past. Absolute dream. Gets it. Is definitely somebody you should always say hello, thank you very much, and just drop a note to her. Definitely worth it.
Yeah, thanks, Chris. Yeah, she's a pleasure working with her.
Well, good deal. That's Ann Gallagher at the FCC. And if you follow that link that I gave you, bit.ly/AM carrier, the very first word after Nautel is Ann Gallagher, where Nautel wrote a letter to Ann to encourage her to approve this technology. Guys, we gotta go. Thanks to Chuck Lukatis, thanks to Chris Tobin, and thanks to Tom Ray for being here on episode 101 of This Week in Radio Tech. Chat room, you're welcome to recommend a title for this show, or if anybody here wants to go ahead and blurt one out, that's fine. I have a quick award to make, and that is, while you guys were talking, I had to quickly go make a random selection. So I closed my eyes and spun my my Android phone around here and put my finger on the retweet that's going to win, and it turned out to be Eisenheimer Engineering, Eisenheimer _ENG. Turns out that's Bill Eisenheimer, and he is I think he's from the San Diego area, but Bill has scored himself a licensed copy of Omnia AXE, audio processing and encoding, that runs as a service on your Windows PC or Windows Server. So, Bill, you hang tight. I'll be in touch with you in the next 12 to 24 hours or so, and we'll get you set up with your prize. Thanks very much for retweeting, and thanks to everybody who retweeted. So now we've got 4 or 5 winners on this contest. So that's it for This Week in Radio Tech. Thanks also to our sponsor, Axia Audio. Go to axiaaudio.com/IQ. Check out the new IQ console. Gotta go. We'll see you next week on This Week in Radio Tech. Bye-bye.